Okay, how do you prove whether something's a basis? First of all, is it linearly independent? And does it span? Okay, so let's start with linear independence, since that's kind of what you addressed. Okay, what's the test for linear independence?
See, the only unique solution for setting the sum of those two expressions is 0.
Okay, so that's a good statement. So there's the test. Look, you always want to write that out, especially if you're in an unfamiliar vector space. Not that you're all unfamiliar with this space. You've done stuff with it, but it's been a little while. Okay? So, we've proven at least a couple of the vector space axioms for this. And we've proven that P2 at least satisfies the most commonly violated axioms. Okay? It turns out it is a vector space, and you will probably prove that for homework. It'll be very easy since you've already essentially proved it. Okay? Okay, so unfamiliar vector space, right there, we want to have that statement, or an equivalent statement. It's a very simple, elegant statement. Okay? Now you said, well, this is a multiple of that. Well, it isn't, but that if it was a multiple, then that would prove it's not linearly independent because it proves this. Okay? Okay, well, anyhow, so this is the same as C1 times x plus 1 plus C2 times x squared plus x equals 0. Okay? So that's the same as C2x squared plus C1 plus C2x plus C1 equals 0. And this would be, has to be for all x. Okay? Now for all x, if this is 0, that means the coefficient of x squared has to be 0. The coefficient of x has to be 0, and the constant has to be 0. Okay? Because if x changes, then what you're multiplying C1 plus C2 by changes, and what you're multiplying C2 by changes by something different. And it comes down to, well, the only way that's going to happen for all values of x is for all three of these things to be equal to 0. Okay? Without going into detail about that, a little more to actually proving that, but we get C2 equals 0, C1 plus C2 equals 0, and C1 equals 0. Right? Well, if C1 equals 0, then C1 plus C2 is just C2, so C2 equals 0. And of course, this one says it equals 0 anyway. Okay? So we've established linear independence. Okay? Now, how do we prove that it spans P2? What do we have to show?
So any arbitrary polynomial P2 can be expressed as a combination of those two.
Okay, so
functions.
exactly. So to prove the span, we say, well, write it this way. There are other ways to write it. Look at the style of proof that the book uses. Look at the style I use, and then choose to use what the book does. Okay? But you understand that by seeing different styles, you develop your own style. You don't have to imitate my style, although any sane person will. You don't have to imitate the book style, okay? Develop your own. And you're doing that, so, okay? And you need some refinement, but that's what we're going to be doing, okay? So, you have this. So how does this look for this basis and this space? Well, it says C1 times x plus 1 plus C2 times x squared plus x equals an arbitrary vector in P2. How do you write an arbitrary vector in P2?
ax squared plus bx plus c.
That's the way I'd write it. So you got to develop your own style, say something different. Okay? Yeah, that's exactly the standard notation that most people would use. But you can use any coefficient you want. A1 x squared plus A2 x plus A3. Okay? That's what we want to use. Okay, so this tells us what? Well, this expression, as we saw here, simplifies to this, right? So we can just jump to that. C2x squared plus C1 plus C2x plus C1 equals AX squared plus BX plus C. Right? So C2 equals A. C1 plus C2 equals B, and C1 equals C. Right? Okay, can you solve that for C1 and C2? Well, if C1 equals C, C2 has to equal B minus C. Right? C2 equals A. Okay. There's no reason A should equal B minus C. Plenty of polynomials in P2. For which A is not equal to B minus C. Matter of fact, almost any polynomial you make up is going to have A not equal to B minus C. Just as a very simple example, x squared plus x plus 1. Clearly A is not equal to B plus C. Okay? B minus C. B minus C is 0. So this is a counterexample. There's your counterexample. So except doesn't span P2. Okay? So it's a really pretty simple proof, and these proofs are typically very simple. Now, the whole thing can also be just expressed in terms of matrices, right? So another way of saying this is, okay, this is a matrix equation, okay, that says that that's this equation, right? Okay? And this equation reduces to this, which tells you C1 equals C2 equals 0, so they're independent, right? Okay, and over here, this matrix equation is this, which reduces down to this, and okay. So you can go to the more compact notation. Right now, I kind of prefer that you write out the simultaneous equations, then write this out and say, now more briefly, this is totally equivalent to saying that this matrix reduces to this, which has no solution for the majority of ABC choices. Okay? There's even more you can say, but that's kind of it. Okay? And then, the fact that you end up with a 3x2 matrix tells you the matrix isn't invertible, which means that in this case, whenever you end up with something like this, you don't have a basis. So if the basis of coefficients that you get out of your simultaneous equations, either for this one or this one, doesn't give you an invertible matrix, you don't have a basis. Either because, or both because you're not linearly independent, or because you've got too many vectors. Okay? Okay, well, there are a lot of connections there. You want to try to see it in as many ways as possible. Okay? Which is something that undergraduates very rarely learn to do very well. Since you're already on track for doing that,